Okay, so now we've had a look at the collisionless Boltzmann equation, right? So when we started from this Boltzmann equation, then we showed, based on homogeneity and isotropy, that we could rewrite that equation into this form. And then we integrated over momentum space to get an equation that looked like this. So the Boltzmann equation, in the limit that we looked at it, implies number conservation. That's essentially the whole physics content of the Boltzmann equation. But of course you might be interested in a particle species that is collisional. In fact, most interesting physics has to do with interactions, right? So we need to be able to treat that in one way or another. And that always implies some kind of approximation scheme, because what we're looking at here is a set of, if you want, classical scalar functions. They don't have any real quantum information. So it's not like a density matrix, for example, that can contain entanglements and so on. So this is very simple. And the question is, how do you treat collisions in such a framework? Well, very schematically, what one can do is to say, okay, the normal collisionless Boltzmann equation looks like this, and then the right-hand side is 0. But in the presence of collisions of one form or another, then the right-hand side should no longer be 0. So it should contain some kind of operator that works on this distribution function. We can call that a collision operator. And the question is, what does it actually do? Well, let's try schematically and look at what collisions do in the context that we look at them here. So you can think of collisions as some unspecified blob, so to speak. Then we have some particle that comes in. That's the one we are interested in. Let's call that 1. And then other stuff goes in as well. We can call these possible other particles 2, 3, 4, and so on. Then stuff comes out on the other side. And let's call this particle I, and then I plus 1 up to n, for example, right? So there can be many particles in the in state. There can be many particles in the out state. Our assumption will be that all particles that come in and go out are free particles. So they are describable as plane waves. So we're working in what you normally know as the Born approximation of scattering. So we have free particles in the in state, free particles in the out state. So that's one thing that we will be assuming. It's possible that this particle I, for example, is identical to particle 1, but with a different momentum. But it could also be a different particle. It could be that if we make this a little bit more concrete and just look at some examples of what I mean by these interactions. So it could, for example, be one where we have, let's see, what could we could have a photon, for example, coming in, but there might be another photon also coming in, and then I might, in the end, have E plus E minus production, right? So that's pair production of electrons and positrons from photons, or pair annihilation if you take it the other way. Then if particle 1 is this photon, then you see there are no particles identical to particle 1 in the out state. So that's certainly one possibility. But it could also be not an annihilation, but a scattering interaction. So it could be another diagram, which is the one we know from Compton scattering, right? That's just scattering on a free electron, where you have a photon coming in, a photon going out again, right? So that's a possibility. Could also be, for example, we could take a diagram like this, where we have 2 photons coming in and 1 photon going out. This is the process known as double Compton scattering. That's also possible. It's certainly a part of this whole formalism. So of course this gets to be very, very complicated, right? So we should now sum over somehow all particles in the initial state, all particles in the final state. which we assume to be free particles. So let's try and see what that actually looks like if we write it out. Let us see. So I have it here. So then that full collision operator for this particle 1, so that should be an operator for not the particle in itself, but for the distribution function. Right. So in here, this must be a rate of change of distribution function, right? So it must be something where you have the effective cross-section for the interaction going into this whole right-hand side. It must also somehow contain the number densities of particles that particle 1 can interact with. And then you must sum over all possible final states that you can think of. Okay, so let's get started. So summation over all states, initial and final, except for the state 1 that we're interested in. Remember, we're working in the continuum limits, so summation is equivalent to integration over momentum space. So that means we must integrate over all other particles that we can have in this interaction, except for particle 1. So somehow there must be this huge, potentially at least huge, phase space integral running all the way from particle 2 up to this particle n that was the final particle in the out state. Then I need to normalize with the phase space volume here. Okay, so that's at least one part of it. Then of course I need to also put in the matrix element for this interaction, right? So I need something like a final state, then an interaction operator of some sort here, an initial state, and then since we're looking at a rate of change, we're looking at a squared amplitude. So that's the amplitude for the process, right? But then I need the absolute square to convert that into a probability. And this is something for my microphysics knowledge, right? So this contains information about the actual type of interaction I'm looking at, electromagnetic, weak, strong, whatever, right? Then I need some normalization factors. And I also need, another important thing, of course, is I need an energy and momentum conserving delta function, right? So I need to sum over only the states that are kinematically accessible. So I must demand that the final state for momentum is equivalent to the initial state for momentum. So that I need to put in as well. And then we're almost there. The only thing that we really need to worry about now is how to properly normalize things. And that's a question of choice, really. So normally, these matrix elements are written in such a way that they end up being dimensionless. And if you do that, then you need to normalize the wave functions in such a way that you automatically get a factor of 1 divided by 2 times energy for each of these things here, including particle 1. So that's one thing. Then we need also, as it turns out, a factor of 2 pi to the 4. Again, that comes from normalization condition. And the final thing is that now, of course, I've summed over all possible momentum states, but that's not really what I'm after. What I'm really after is I need to sum over all the states where I have particles. And that means I have to weigh this with the distribution functions in some way. So now we're looking at a process, remember, where I have particles 1, 2, and so on, up to particle, let's say I minus 1 in the in state, and then I have particle I up to n in the out state. Right, so if I have the process running from left to right, that means I need to, in each of these things here, I need to multiply with the distribution function, starting all the way from 1 and up to I minus 1, right? So I need something like f1 blah 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 up to fi minus 1. And then remember, if I run from left to right, I'm actually taking a weight distribution function. So I need a minus sign here. But that's not all. I also, in principle at least, I need to worry about whether there are filled states in the out state. Right? So for example, if the particles I produce are fermions, then I need to worry about Pauli blocking. If they're bosons, I need to worry about stimulated emission. And that all comes down to factors that I need to put in here. So as it turns out, I get factors of 1 plus minus the distribution function for all the rest of the states, all the ones going up to n, like this. So for example, if I have a completely degenerate Fermi C in the out state, then all these terms are 0, right? Because for a degenerate particle species, the distribution function is a box which is 1 up to the Fermi level and 0 above. And that means unless I can kick the particle above the Fermi level, this interaction doesn't happen because it has no accessible final state. In cosmology, that's never the case because particles are always dilute and never degenerate. But these Pauli blocking or stimulated emission factors can typically give corrections up to 10% or so, maybe 20% in some cases for these interactions. Okay, so we're almost there. Except, of course, I now also have to worry about the process running from right to left. And that means I have to completely mirror what I have here. So I now have a plus, and then I count all the states from I up to n. And then I have my Pauli or stimulated emission factors for all the other states up to I minus 1. So that's what the collision operator looks like in this approximation where I treat particles as always being free and I use the Born approximation for scattering. Then I get this and it looks really nasty and complicated, right? So it's not something that you really want to have to deal with because it's immensely complicated to do. Now, one final little thing is that instead of working with this full collision operator, actually the way Dodelson does it and the way people often do it is to work with the integrated Boltzmann equation. So we carry out one final little momentum integration, namely the 1 over P1, because that symmetrizes everything, right? So then I have d3 P1 like this. And then you see it looks fully symmetric under all of these indices. And now I can plug that together with the left-hand side of the Boltzmann equation, which I now, in the integrated version, know to be given by this. Okay, so that's the very nasty looking answer to what the collision operator actually is. And this is the starting point for the discussion in Dodelson chapter 3. So this is Dodelson's chapter or equation 3.1, where the left-hand side is given by what I have over there, and the right-hand side is this big and nasty looking thing. And the next step is to actually try to simplify this collision operator until it takes a form where we can get a little bit of intuition for what it does. So that's the next step.